Hi there, this is the last video where we're going to be talking about transformation matrices and just a few things to fill in the gaps here, particularly around shears. It's one of the things that the syllabus mentions here, that we've got rotations, reflections, dilations and shears. So I want to talk about what a shear is and what the matrix is that represents a shear, and then just a few extra examples to fill in. Okay, so let's have a look at what a shear does. We've got this unit square here. You can see what I'm going to do is create a shear along the x-axis, and that is a shear of shear factor 1. Now I'm going to just increase that so you can see what happens as I increase the shear. This is now a shear factor of 2. So you can see the layers are kind of sliding across there. You'll notice that the invariant line here is the x-axis, so any points that are on the x-axis do not move, but everything above the x-axis does move. Now that's a shear factor of 3, so you can see this point here has moved 3 places over to the right, and it is 1 away from the invariant line, and that's how you get the shear factor. The shear factor is given by this formula: the distance the point moves divided by the distance the point is from the invariant line. So if I change the distance from the invariant line now, you can see the point goes way over there. Okay, so let me bring it back. This is now a shear factor of 2. So this point here is 2 away from the invariant line, and it has moved 4 places to the right. Okay, so that's the formula that you use for a shear. This is now a shear factor of 1, a shear factor of 1/2. So that divided by that is now 1/2, and that's the same for every point. There's a shear factor of 0, which is pretty boring, and if we go into the negative, we just move it over to the left. So it's the same thing. Shear factor of -1, the point moves 2 to the left, and it's 2 away from the invariant line. This point here moves 1 to the left, and it's 1 away from the invariant line. Okay, let's look at what a shear would look like if you sheared it where the y-axis was the invariant line. So we're kind of stretching it up here. So here's what the shear would look like. Here is a shear factor of 1. So again, the formula is the distance this point here moves divided by the distance it is from the invariant line. So you can see that's moved 1, it's 1 away. So the shear factor here is 1. If I keep going up to 2, you can see now this point has moved 2 up, and it's 1 away from the invariant line. Again, if I just change the coordinates of that point there, this point here is 2 away from the invariant line, and it has moved 4 places up. So that is 4 divided by 2, so the shear factor here is 2. Now if I bring it back down again you can see the idea. Here's a shear factor of 0, and if we go negative, then the shear just goes down in the downward direction. Just like when we had with the x-axis, it was right for positive, left for negative. Same with shears along the y-axis, positive up and negative going down. So that's a shear factor -1 parallel to the y-axis. That one was there. Okay, so now let's look at what the matrix looks like when we're performing a shear. So here we've got a shear factor of 2 where the x-axis is the invariant line. So we've taken our unit square, all these unit vectors, and we've sheared it across with a shear factor of 2. So you can see the point 1, 0 stays where it is, it's on the invariant line, but the point 0, 1 has moved 2 places across. Okay, the point that was at 1, 1 has moved 2 places across to 3, 1. So that divided by that is 2. Okay, so that is a shear factor of 2. Now what's the matrix that represents that transformation? Again, I think the easiest way is to just consider those unit vectors and see what happens. So the point 1, 0 stays where it is, so it stays at 1, 0. The point 0, 1, on the other hand, so that's this point here, 0, 1, has moved to 2, 1. So that is the second column in your matrix there. So this is the matrix that represents a shear factor 2. It's not too much of a stretch then to suggest that this is the general matrix for all shears that are parallel to the x-axis, and K is your shear factor. If you wanted to get a matrix where you were shearing on the y-axis, it would look like that, where K is the shear factor, so 1, 0, K, 1. So you can see in this example here we've got a number of shapes and it's asking us what matrix produces those shapes. So we've done these before. I particularly want to look at A to D because A to D is a shear. So if we just look at A to B, a bit of revision, how do we get from triangle A to B? Just this is a reflection in the x-axis. So what is the matrix that gives us a reflection in the x-axis? Start with my identity matrix. What happens to 1, 0 when we do a reflection in the x-axis? It stays exactly where it is. What happens to the point 0, 1 when we do a reflection in the x-axis? Well, that becomes 0, negative 1. Simple as that. That's the answer to the first one. That's the matrix. And we've already done how to do shears, but if you look at this one here and just look at a few points to see, this point here is 1 away from the invariant line and it's moved 2. So 2 divided by 1. This point here has moved 2 divided by 1. This point here has moved 8 divided by 4. So in each case I can see the shear factor is 2. Okay, the distance that's moved divided by the distance from the invariant line. So this is a shear factor 2. Now if you don't remember what that matrix is, you can go through the same process that I did, and that is just looking at the unit vectors and seeing what you get to get the correct answer, which is that for your shear factor 2. Okay, lastly, a few interesting problems, and you can see hopefully when I do these how useful this is if you're talking about graphics and TV graphics. So we've got this matrix here, and this matrix transforms all points on the plane to the line y equals minus 2x. So that's cool, so we've got points everywhere. You can see that by using a matrix transformation, all of these points are going to snap onto a straight line with a gradient of negative 2 going through the origin. So here's the proof. 3, negative 1, negative 6, 2 is the matrix. Let's say A and B are our points in the xy plane. So A and B could be any point. So now multiplying the matrix, we've got 3A minus B for the top one and negative 6A plus 2B for the bottom one. So when we apply that matrix to any point, this is the matrix we get. Now if I rewrite that matrix there to 3A minus B, and you can see if I take out negative 2 and factorise, we get that for the bottom one, so negative 6A plus 2B, right? So you can see just looking at this matrix here that the x values, or the y values I should say at the bottom line, the y value there, that's this thing here, is just equal to negative 2 times the x value, and that's always going to be the case. Y value is always negative 2 times the x value, so therefore all of the points are transformed to the points along that, different points along that line. Similar question here, when we've now got the points on a line transformed by a matrix, and we're asked to find what the equation of that image line is. So matrices also take all the points on a line and transform them to another line. Well, this matrix does that. So we've got 1, 2, 1, 0. Now let's look at any general point on this line y equals 2x minus 3. So if we say the y value is, let's say, k, sorry, the x value is like k, then the y value is just going to be 2k minus 3. So that matrix there will describe all of the points on this line with an x value of k and a y value of 2k minus 3. So let's look what happens when we multiply those two together. So we get 1 times k plus 2 lots of 2k minus 3 for the top entry. And the bottom entry we've just got k. Pretty simple. So simplifying the top, we've got k plus 4k, that's 5k, minus 6, and k. Alright, so when we perform this transformation, all the points end up like this. So the x values are 5k minus 6, and the y value is just k. So if we eliminate k from these two equations here, we then get the equation in terms of just x and y. So that's pretty simple to do. Replace k for y in that one, and we get x equals 5y minus 6. So a little bit of rearranging. That's the equation of our line, y equals x plus 6 divided by 5, or x divided by 5 plus 6 over 5. That's the equation of the image line in this transformation.